Have you ever stopped to think about what makes modern structures so strong? I mean, from those incredible skyscrapers that seem to just pierce the clouds?
To the bridges that span these huge distances.
It's pretty mind-blowing when you think about it.
Yeah, it really is.
And, behind all of those structures, there's a ton of engineering going on,
A ton.
making sure they are safe and can withstand all kinds of loads and forces.
Right.
And a lot of those engineering principles that make it all possible can be traced back to one person.
To one person.
One person. Stephen Timoshenko.
Oh, wow. Yeah, I've definitely heard that name.
Oh, yeah.
In a lot of my engineering courses, actually.
Absolutely. He's considered the father of modern structural engineering.
Interesting.
And on this deep dive, we're going to really try to understand why that is.
I'm excited.
We're going to explore his work, his impact, and especially how he's influenced engineers like you and me today.
Awesome. Yeah, I'm really interested in seeing how his work from so long ago is still relevant to what we're doing today.
Exactly. That's the big question, isn't it? So to get into all of this, we've got some great material to work with.
What are we looking at?
Well, we've got excerpts from some of his own books.
Oh, cool. So we get his insights directly from the source.
Exactly, like Elements of Strength of Materials, which is a classic.
Oh, yeah, I remember that one from school.
And we've also got History of Strength of Materials, which I'm really excited to dig into.
Oh, that sounds fascinating.
And, of course, his Wikipedia page to fill in some biographical details and get a sense of his wider impact.
Sounds like a great collection of sources.
So the mission today is to give you, the listener, a really clear understanding of what made Timoshenko so important to engineering.
We want to connect his work to what engineers are doing today.
And maybe uncover some surprising facts along the way.
I love those.
So let's start at the beginning. Where did this engineering giant come from?
Well, Stephen Timoshenko was born Stepan Prokopovich Timoshenko in 1878
Okay.
in Ukraine,
Ukraine.
which back then was part of the Russian Empire.
Got it.
So he got his early education at the St. Petersburg State Transport University.
That's a pretty prestigious school, isn't it?
Oh yeah, a major institution, especially for engineering.
So he had a solid foundation in engineering principles right from the start.
Definitely. But there's another interesting part of his education that comes a little later.
Oh, really? What's that?
He spent a year at the University of Göttingen,
Okay.
studying under Ludwig Prandtl.
Prandtl. Now that's a name that rings a bell.
Prandtl was huge in fluid mechanics,
Right.
but he also made big contributions to applied mechanics in general.
So Timoshenko had this blend of Russian and German engineering thought influencing him.
That's right. You can really see how both of those traditions shaped his thinking.
It's like a cross-pollination of ideas leading to something new and innovative.
Exactly. And you see that in all of his work, this blend of theory and practical application.
That's fascinating.
So, he didn't immediately jump into research after his studies.
Oh, so what does she do?
She actually started out teaching.
Teaching. Oh, wow.
Yet he held positions at the Kiev Polytechnic Institute
Okay.
and the St. Petersburg Polytechnic University.
So he was deeply involved in education from the start.
Right from the start. And that commitment to teaching really shows his dedication to engineering.
And to shaping the next generation of engineers.
Exactly. And it's actually during those early years that he starts making some significant contributions.
Oh, really? I thought his major breakthroughs came later.
They did, but even back then he was doing important work.
Like what?
Well, he did some really groundbreaking work on buckling.
Buckling.
Understanding how structures fail under compression.
Oh, right. That makes sense.
And get this, he also published the first version of his famous Strength of Materials textbook during that time.
No way.
Yes, while he was at the Kiev Polytechnic Institute.
So even in those early years, he was already having a huge impact on engineering education.
Absolutely. That textbook became a classic, and you can see his influence starting to take shape.
I can only imagine how many engineering students have learned from that book over the years.
Countless.
So we've talked about his early life and his start in teaching.
We've seen those early contributions.
But how did he become this foundational figure in engineering mechanics?
Right, how did he get there?
What are the key contributions that really solidified his place in the field?
Well, to understand that, we need to go back to the basics, the core concept of strength of materials.
Strength of materials.
Okay. Timoshenko himself defines it really well in his book, History of Strength of Materials.
Oh, perfect. Let's hear it.
He says strength of materials is that branch of engineering concerned with the deformation and disruption of solids when forces other than changes in position or equilibrium are acting upon them.
Wow. Okay. That's a pretty dense definition.
Yeah, it is. But it's really important because it lays the foundation for everything else.
So it's about how materials behave under stress, how they deform, how they resist breaking.
Exactly, and that's crucial for designing anything that needs to withstand any kind of load.
Right, from bridges to buildings to
Through
aircraft.
everything.
So Timoshenko didn't just describe what others had already figured out.
He actually pushed the field forward.
In what way?
Well, one of his most important contributions is the Timoshenko beam theory,
Ah, yes, the famous Timoshenko beam theory.
which he developed with Paul Ehrenfest.
Okay, so what makes this theory so special?
Well, before Timoshenko, engineers used the Euler-Bernoulli beam theory,
Right.
which worked fine for many cases, but it had some limitations.
Limitations like what?
Well, it made some simplifying assumptions about how beams deform,
I see.
and those assumptions didn't hold true for all situations.
Okay.
So the Timoshenko beam theory came along, and it was a more accurate model because it took into account things that the Euler-Bernoulli theory didn't, like shear deformation and rotary inertia.
Okay, so can we break those down a bit?
Sure, so shear deformation is like when the cross-sections of a beam, they kind of warp and slide past each other.
I see.
And rotary inertia is about the resistance of a beam's mass to changes in rotation. Now, these factors are especially important for certain types of beams.
Which types?
Short, deep beams, or beams under high-frequency vibrations or impact loads.
So the Euler-Bernoulli theory wouldn't be as accurate in those cases,
Right, it can underestimate the stress and deflection.
making it potentially unsafe.
Exactly.
But the Timoshenko theory gives engineers a more realistic picture,
And a more reliable way to design those beams.
so they can be confident that their structures will hold up.
Exact.
And it's not just beam theory that he made contributions to.
Oh, no, he did a lot more.
Like what?
He made major advancements in the theory of elasticity,
Theory of elasticity.
which is basically the math behind how solid objects deform under stress.
So he was developing the tools that engineers still use today to analyze those complex forces.
He was laying the foundation.
Incredible. And all of this was happening in Europe, right?
Right, but then his career takes a really interesting turn.
What happened?
He emigrates to the United States
To the U.S. Wow, in what year?
in 1922.
Okay, so what did he do in the U.S.?
Well, he first worked at Westinghouse Electric Corporation for a bit.
Westinghouse. So was he applying his theories to real-world engineering problems?
Yeah, likely working on their electrical equipment and power systems.
I see.
But his biggest impact in the U.S. came when he joined the University of Michigan.
University of Michigan.
And get this, he created the first bachelor's and doctoral programs in engineering mechanics in the country.
Wow. So he wasn't just teaching, he was building a whole new field of study.
Exactly. He was shaping how engineering was taught in the U.S.
That's a massive contribution.
Huge.
And he didn't stop there, did he?
Nope. In 1936, he moved to Stanford University.
Stanford, another prestigious institution.
Absolutely. And he continued to have a major impact on engineering education and research there.
I bet he had some pretty impressive students, too.
Oh, you have no idea. Some of his doctoral students went on to become giants in the field themselves.
Like who?
Nicholas J. Hoff, James N. Goodyear, Igor Popov, just to name a few.
Wow, those are big names in engineering.
Big names, and it shows how his influence spread through generations of engineers.
It's like a ripple effect.
Exactly. His ideas, his rigor, his passion for engineering all passed down through his students.
That's really powerful, and we can't forget about his textbooks.
The textbooks, oh yeah, those are legendary.
Like Strength of Materials? I mean, that's practically the Bible for engineers.
Pretty much. And it wasn't just Strength of Materials. He wrote several influential textbooks.
Like?
Theory of Elasticity, Vibration Problems in Engineering, Elements of Strength of Materials.
And those books have been used all over the world, haven't they?
All over the world, they've been translated into 36 languages.
36 languages. That's
Yeah.
insane.
It is, think about how many engineers have learned the fundamentals of their profession from those books.
It's just mind-blowing.
J.P. Den Hartog, who worked with Timoshenko at Westinghouse, said that Timoshenko's name is known to nearly every mechanical and civil engineer in the entire world.
Wow, that really sums it up, doesn't it?
Yeah, it does. His influence is just massive. And he even wrote an autobiography, as I remember.
Oh, cool. So we get a personal glimpse into his life and thoughts.
Exactly. It's a fascinating read.
So we've got this brilliant researcher, incredible teacher, and prolific author all in one person.
And he gets recognized for all of it.
Oh, I bet he racked up some awards.
Oh, yeah. In 1957, the American Society of Mechanical Engineers, ASME, created the Timoshenko Medal in his honor.
And guess who the first recipient was?
I'm going to guess Stephen Timoshenko.
You got it.
Of course.
It's still one of the highest honors in applied mechanics,
It recognizes distinguished contributions to the field.
which perfectly describes Timoshenko's career.
Perfectly.
And the recognition didn't stop there, did it?
No, he was elected to prestigious scientific societies like the American Philosophical Society
Wow.
and the United States National Academy of Sciences.
So he was recognized by the broader scientific community as well.
Absolutely. And in Ukraine, the Institute of Mechanics of the Ukrainian Academy of Sciences is named after him.
That's amazing. His legacy lives on in so many ways.
It really does. And there's even an archive of his manuscripts and letters.
Oh, wow. So researchers can still study his work in detail.
Exactly. His impact continues to be felt.
So we've covered a lot of ground here.
We have.
But the big question is, how does all of this connect to engineers today?
Right. How is Timoshenko's work still relevant in the 21st century?
Exactly.
Well, here's the thing. The theories and principles he developed are still the foundation of so much of what we do.
Really, even with all the advanced software and technology we have now.
Even with all of that, when we use those tools to analyze and design structures, the underlying algorithms, the math behind it all, a lot of that goes back to Timoshenko.
Wow. So he's like the unseen architect of modern structural engineering.
In a way, yes, his work is built into the very fabric of our designs.
That's incredible. Can you give us a specific example?
Sure, take the Timoshenko beam theory, for instance.
Okay.
It's still crucial for things like aerospace engineering,
Aerospace, that makes sense.
where they need to design lightweight but incredibly strong components, or in high-speed rotating machinery, where you have to analyze vibrations very carefully.
So in those situations, the Timoshenko theory gives engineers the accuracy they need
Absolutely.
to make sure their designs are safe and reliable.
Exactly.
It's fascinating to think that a theory developed so long ago is still so vital today.
It speaks to the power of fundamental principles.
And it's not just the advanced theories.
Right.
His textbooks are still widely used, too.
Absolutely, both by students learning the basics and by practicing engineers.
Who need to refresh their knowledge or tackle a challenging problem.
Exactly.
So his influence is really multifaceted.
It's research, it's teaching, it's textbooks, it's all connected.
And it's all had a profound impact on the field.
Profound.
It's inspiring to think about his journey
It is.
from his early life in Ukraine to becoming a global leader in engineering.
Overcoming so many challenges along the way.
His dedication to understanding structures and to teaching others is really remarkable.
It's a great example for all of us in the field.
I think his legacy goes beyond just the specific formulas and theories he developed.
I agree.
It's that spirit of inquiry, that drive to understand the world around us.
And to use that understanding to build new and better things.
That's something that can inspire engineers for generations to come.
Absolutely. And it makes you wonder what new foundations today's engineers will lay,
What breakthroughs are waiting to be discovered?
building on the incredible work that Timoshenko started.
That's a great question to ponder.
It is.
And if you're interested in learning more about Timoshenko, or structural engineering in general,
Or the history of the field.
we encourage you to dig deeper.
There's so much out there to explore.
And you might be surprised by how relevant Timoshenko's work still is today.
You might see connections to modern engineering marvels that you never noticed before.
So keep exploring and keep learning.
Keep pushing the boundaries.
And who knows, maybe you'll be the next Timoshenko,
Would be.
leaving your own mark on the world of engineering.
It's an exciting thought.
It is.
Thanks for joining me on this deep dive.
It was a pleasure having you.
I always learn something new on these deep dives.
Me too.
Until next time.
Take care.